What if the real reason we may never travel among the stars is not money, politics, or imagination, but the universe itself? For decades, science fiction made interstellar travel feel inevitable. But when we face the true scale of space, the limits of speed, fuel, radiation, time, and survival, the dream begins to look far more terrifying. The stars may not be waiting for us. They may be locked behind barriers built into reality itself. Today, we uncover the brutal truth behind humanity's impossible dream of reaching other stars. Let's begin. If you shrink the distance from Earth to Alpha Centauri down by a factor of 1 billion, it would still stretch over 4,000 kilometers. That is nearly 1.5 times the distance from New York to Los Angeles. That is the shrunken map. The real one, the actual distance sitting out there right now, is 41 trillion kilometers. That is the map we are talking about crossing. We named this thing space, not the abyss, not the void, not the environment that will dismantle you, without a moment's hesitation. We called it space, a word that sounds open, comfortable, generous, like a room with extra room. And that single word has done more damage to human ambition than any failed rocket launch in history. Because the truth is the opposite. Space is the most hostile environment in the entire observable universe. It doesn't threaten, it doesn't warn, it simply ends things. Here is what actually happens to a human body the moment it meets unprotected vacuum. Vacuum doesn't wait, it pulls. The gases dissolved in your bloodstream begin forming bubbles in your veins as external pressure vanishes. Your lungs, if you make the instinctive mistake of holding your breath, rupture from the inside as expanding air tears through tissue. The moisture on your tongue, in your eyes, lining every airway, flash evaporates, not slowly, not dramatically. Like in the movies, within roughly 15 seconds, oxygen delivery to your brain collapses. Circulation begins to fail. You don't freeze. You don't explode. You simply stop working, systematically, irreversibly. Quick question before we go further. How long do you think a person actually survives unprotected in space? 1 minute. 5 minutes? 15 seconds to incapacitation. 90 seconds to the point of no return. Not 5 minutes, not 1 minute. 15 seconds. Now, here's the part that breaks the mental picture most people carry. The background temperature of the universe is negative 270.45 degrees Celsius, 2.7 Kelvin, barely above absolute zero, colder than anywhere on Earth by a staggering margin. You'd expect instant freezing, but in true vacuum, there is no medium to conduct heat away from you. No air, no water, no substance to carry thermal energy off your skin. Heat only escapes through radiation, and radiation is slow. So while your vascular system is failing from zero pressure, one side of your body is simultaneously being struck by unfiltered solar radiation at over 1,300 watts per square meter, while the side facing shadow drifts toward that 2.7 Kelvin baseline, burning on one side, freezing on the other. Same moment. The universe isn't cruel, it's indifferent, and at this scale, indifference and cruelty are impossible to tell apart. NASA has spent billions of dollars across multiple generations of engineering to design suits capable of keeping one person alive for a few hours outside a spacecraft. A significant portion of that budget, across decades of iteration, went toward solving the problem of how an astronaut urinates correctly in zero gravity without contaminating life support systems. Not propulsion, not navigation, waste management, billions of dollars and years of research dedicated to one biological function. Every human performs automatically on Earth without a second thought. That is precisely how friendly this environment is. On Earth, you are surrounded by a support system so complete you have never once had to notice it. Fuel is 2 exits down the highway. A hospital is 40 minutes away. The atmosphere holds pressure against your body constantly, at no cost, without requiring your attention. The magnetic field wraps around the entire planet, deflecting the worst of what the sun throws at it. Temperature stays within the range your biology was built for. Every single day, Earth is running thousands of parallel systems to keep you alive, and you never have to ask it to. Leave for another star, and every single one of those systems disappears. You carry everything, or you die. There is no resupply. There is no rescue. A distress call sent from interstellar space travels at the speed of light, and the nearest star is over 4 light years away. Your signal arrives 4 years after you sent it. Any response takes another 4 years to reach you. 8 years of silence, while whatever went wrong finishes going wrong, without any possibility of intervention. Walking across the Sahara alone, no water, no map, no phone is a reasonable picture of extreme survival. But the Sahara has air. It has gravity keeping your blood where biology intended. It has ground beneath your feet, and the theoretical possibility of another human being just past the next dune. Space offers none of these. Take everything that makes Sahara survival conceivable and remove it one element at a time, and you start approaching what interstellar travel actually demands of the human body. None of this is an argument for stopping. None of it means the question stops being worth asking. But there is a version of this story where humanity spends generations drawing blueprints, funding missions, writing fiction, genuinely believing the stars are just a long flight away if only the right ship gets built. That version rests on a comfortable illusion, and physics has no interest in comfortable illusions. But if vacuum is just the opening problem, the welcome mat at the front door, then distance is the wall behind it. And that wall wasn't built from rock or steel. It was built from the laws of physics themselves, and it has never once made an exception for anyone. Sunlight takes 8 minutes and 20 seconds to reach Earth, 8 minutes and 20 seconds to cross 150 million kilometers, and we call that fast. Because by human standards, it genuinely is. You flip a light switch, and the room fills in a fraction of a nanosecond. Light covers the distance from here to the moon in just over 1 second. It feels instantaneous. It feels like the closest thing to everywhere at once that physics allows. Hold that feeling, because it's about to be taken apart piece by piece. Light from Alpha Centauri, the nearest star system to our own, the closest neighbor we have in this entire galaxy, takes 4.24 years to reach us. Not 4.24 days. Not 4.24 months, 4.24 years, traveling at 299,792 kilometers per second, without slowing down, without stopping, without taking a single detour. That light left its source before many of the people watching this were born, and it is only just arriving now. Every time you look at Alpha Centauri in the night sky, you're not seeing it as it is. You're seeing it as it was 4 years ago. The star you're looking at might not even exist anymore. You'd have no way of knowing for another 4 years. Voyager won the fastest human-made object ever launched. Still traveling. Still transmitting faint signals back to Earth after nearly 5 decades in space, moves at roughly 61,000 kilometers per hour. It is the farthest any human creation has ever traveled. Engineers at NASA track it daily with quiet pride. It has crossed into interstellar space, beyond the boundary of our solar system's influence. We speak of it as our great emissary to the cosmos. At that speed, Voyager 1 would need 73,000 years to reach Alpha Centauri. Not 73,000 days. 73,000 years. Homo sapiens as a species has only existed for roughly 300,000 years. So the fastest thing we ever built would spend nearly a quarter of our entire species' existence in transit just to reach the nearest star, and it still wouldn't arrive. The pyramids of Giza were constructed roughly 4,500 years ago. 73,000 years is more than 16 times that. It is a number so large it stops feeling like time and starts feeling like geology. The natural response is, we just need to go faster, build better engines, push harder. The speed of light is fast, so aim for that. Close the gap with ambition and engineering. And this is exactly where the universe closes the door, quietly, permanently. The speed of light is not a technical limitation. It is not a barrier that better engineering will eventually overcome. The way we broke the sound barrier in 1947 or learned to escape Earth's gravity, the speed of light is a structural feature of reality itself. Einstein's most famous equation, energy equals mass times the speed of light squared, reveals something devastating. When you follow it to its logical conclusion, as any object with mass accelerates toward the speed of light, the energy required to keep accelerating does not simply increase. It approaches infinity, literally, mathematically, without ambiguity. An object with mass cannot reach the speed of light because doing so would require infinite energy. And infinite energy does not exist. This is not a funding problem. It is not a materials problem. It is not something a better rocket solves. It is written into the fabric of space-time, and it carries no exception clause for determined species with big dreams. Quick question: if a spacecraft could somehow travel at the speed of light, how long do you think it would take to reach the center of the Milky Way? 26,000 years. That is the distance to the galactic center. 26,000 years at the maximum speed the universe permits for anything with mass. And we are nowhere near that speed, not remotely close. The Milky Way galaxy. Our galaxy, the one containing our sun. Our solar system? Everything any human has ever seen with naked eyes is 100,000 light years in diameter, even at light speed. Crossing it edge to edge takes 100,000 years. The entire recorded history of human civilization, from the first writing systems in ancient Mesopotamia to everything happening on Earth right now, spans roughly 5,000 years. To cross our own galaxy at the speed of light would take 20 times that entire history. At any realistic speed available to us today, the number becomes so large it loses all meaning as a measurement of time and becomes simply a synonym for never. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. The observable universe stretches approximately 93 billion light-years across. But here is the part that closes the last theoretical door. Most of it is already permanently unreachable. The universe is expanding. The most distant regions are being carried away from us faster than the speed of light, not because anything is moving through space faster than light, which relativity forbids, but because space itself is expanding, stretching the distance between us and those regions at a rate that exceeds light speed. That is a different mechanism entirely, and it has no known workaround. Those regions are not just far, they are causally disconnected from us. No signal, no ship, no information of any kind will ever bridge that gap, regardless of how advanced a civilization becomes. They are gone from our reachable universe in every meaningful sense. To feel that scale without the numbers collapsing into abstraction, imagine Earth is a grain of sand sitting on a beach in New York City. At that scale, Alpha Centauri is another grain of sand sitting on a beach in Los Angeles. 2 grains of sand, roughly 3,000 kilometers apart, and between them, nothing. No rest stops, no fuel depots, no emergency services, no possibility of rescue if something goes wrong at the midpoint. Just unbroken vacuum, cosmic radiation, and the indifferent arithmetic of distance. We named our most beloved science fiction franchise Star Wars. Wars among the stars. Entire fleets jumping between solar systems. Battles fought across galaxies. Heroes making the Kessel Run in under 12 parsecs, as if distance were merely an inconvenience. It is magnificent storytelling. But reaching the nearest star to our own is already a war we would lose before the first engine fired. The enemy is not another civilization. The enemy is distance itself, and distance has been winning since the first second after the Big Bang. But suppose someone accepts all of this and says, fine, thousands of years, hundreds of thousands of years, we will work with that time scale. Just tell us what our best propulsion technology can actually do right now. Show us the numbers. What does the cutting edge of human engineering look like pointed at the stars? The answer will make you want to close every aerospace budget spreadsheet you've ever seen and go lie down quietly in a dark room. Saturn V, the most magnificent machine human beings have ever built. 36 stories tall, 2.8 million kilograms of controlled explosion pointed vertically at the sky. When it launched Apollo 11 in July of 1969, the sound pressure alone shook the ground for kilometers in every direction, rattled windows across the Florida coastline, and sent 3 human beings toward the moon for the first time in the 4-billion-year history of life on this planet. Over half a century later, it remains the most powerful rocket ever successfully flown. Engineers who witnessed the launches describe the experience as something closer to a geological event than a machine firing. It is the crown jewel of human technological achievement in space. Saturn V reached a top speed of approximately 11 kilometers per second. The speed of light is 299,792 kilometers per second. That means Saturn V traveled at roughly 0.004% the speed of light. Not 4%, not 0.4%, 0.004%. The most powerful rocket in human history. The machine that put footprints on the moon and defined an entire era of human ambition barely registers as a rounding error on the scale of interstellar travel. At that speed, a journey to Alpha Centauri would take approximately 115,000 years. 115,000 years aboard a vehicle we consider the pinnacle of propulsion engineering. Perhaps rockets are the wrong measure. Let's look at the fastest human-made object currently operating anywhere in the solar system, the Parker Solar Probe. Launched by NASA in 2018 and designed to study the sun's outer corona at close range, achieves speeds approaching 690,000 kilometers per hour during its closest solar passes. It is genuinely the fastest thing humanity has ever built, a number that sounds almost violent in its magnitude. It still only reaches 0.064% the speed of light. At that velocity, a journey to Alpha Centauri would take approximately 6,600 years. 6,600 years. The Roman Empire fell less than 1,600 years ago. The Wright brothers flew at Kitty Hawk only 121 years ago. We are talking about a journey to our nearest neighbor that would require more time than 4 Roman empires laid end to end across history. So, quick question. What do you think the most ambitious interstellar mission humanity has ever seriously proposed actually weighs a crewed spacecraft, an unmanned probe the size of a car, a satellite, a few grams? That is the answer. Breakthrough Starshot, announced in 2016 with backing from prominent scientists and substantial private funding. With the late Stephen Hawking among its most visible early supporters, proposes sending a postage stamp-sized chip, fitted with a microscopically thin light sail, accelerated by a ground-based laser array, generating 100 gigawatts of continuous power. In theory, that chip reaches 20% of the speed of light. At that velocity, it arrives at Alpha Centauri in approximately 20 years. 20 years. For the first time in this entire conversation, a number that sounds almost human in scale, almost achievable, almost real. Then you look at what the chip actually is. It cannot slow down. There is no braking system, no deceleration mechanism of any kind, because slowing down would require the same laser array pushing from the other direction and there is no such array at Alpha Centauri. The chip flies through the system at 20% the speed of light and keeps going forever. Its window for any meaningful observation during closest approach lasts approximately 1 hour. The data it transmits travels back to Earth at light speed, meaning it arrives 4.24 years after being sent. You would launch the chip, wait 20 years for it to arrive, then wait another 4 years for the first images to reach you. And as of today, the entire project exists only on paper. No functional prototype has been launched. The 100 gigawatt laser array does not exist. And the engineering required to build a coherent beam system capable of tracking a gram-scale sail through Earth's atmosphere at the necessary precision remains an unsolved problem. But none of that is even the sharpest point. The chip cannot carry a human being. It cannot carry food, water, or breathable air. It cannot carry a single living cell, not a bacterium, not a fungal spore, not the simplest microorganism biology has ever produced. It carries miniaturized instruments and a transmitter. Nothing on it breathes. Nothing on it has a heartbeat. Nothing on it experiences the journey in any sense whatsoever. Sending a chip to another star is like firing a sticky note across the Pacific Ocean with a rubber band and declaring the conquest of the sea. The note might make it. It might even send back a photograph of the other coastline. But you did not cross the ocean. The ocean remains exactly as vast, exactly as impassable, exactly as indifferent to your ambitions as it was before you picked up the rubber band and called it a mission. Breakthrough Starshot is fundamentally a plan to launch something smaller than a human fingernail into interstellar space and label it humanity's first interstellar expedition. Somewhere, Einstein is raising one very specific eyebrow at the press release. So microscale is out. If the answer isn't a chip, it must be a ship, a real one, large enough for people, for food systems, for air recycling, for the entire apparatus of human survival across centuries. A generation ship, the grandest engineering project conceivable, carrying not just passengers, but entire communities, entire societies, entire lineages, born and living and dying aboard a vessel moving between stars. It sounds like the opening of humanity's greatest chapter. And it is right up until you examine honestly what happens inside that ship after 200 years. What you find there is not a civilization in motion. It is something far darker and entirely inevitable. A generation ship. The concept has lived in science fiction for nearly a century. A vessel the size of a small city, carrying thousands of people, launched toward a distant star with the understanding that the crew who departs will never arrive. Their children won't arrive either, nor their grandchildren. The people who finally set foot on another world will be separated from the original voyagers by a dozen generations or more, born into a mission they inherited rather than chose, living their entire lives inside a metal container, moving through the dark between stars. It sounds like the grandest epic in human history. It sounds like the opening of a story that spans centuries and ends in triumph. It sounds that way until you run the actual numbers. Start with biology, because biology doesn't care about the story. Geneticist Cameron Smith at Portland State University published research in 2014 examining exactly what population size a generation ship would need to maintain viable genetic diversity across a multi-generational voyage. His conclusion? A minimum of 10,000 individuals, with 40,000 being a more robust target to buffer against disease outbreaks, accidents, and random genetic drift. Fall below that threshold, and the consequences are predictable and irreversible. Inbreeding depression accelerates. Recessive genetic disorders accumulate across generations. Fertility rates decline. Infant mortality rises. And within a few centuries, the population collapses from the inside, not from any external catastrophe. simply from the mathematics of a gene pool too small to sustain itself across deep time. 10,000 people, minimum, on a ship, for potentially thousands of years. The engineering requirements for keeping 10,000 human beings alive in a sealed environment for that duration: food, water, atmosphere, waste processing, medical care, structural integrity, are so far beyond anything we have ever built that they belong in a different category of challenge entirely. But set the engineering aside for a moment, because something else goes wrong first. The human mind was not built for this. Every significant study of long-duration isolation tells the same story. Crew members aboard the International Space Station, despite video calls home, despite regular resupply missions, despite knowing their isolation ends in 6 months, consistently report depression, interpersonal friction, motivational collapse, and cognitive fatigue. Submarine crews operating on 90-day deployments show measurable psychological deterioration by the final weeks. The Mars 500 experiment, conducted between 2010 and 2011, locked 6 volunteers in a facility simulating a Mars mission for 520 days, the longest controlled isolation study ever run. Results showed sedentary behavior increasing dramatically, sleep disruption, psychological withdrawal, and significant declines in group cohesion as the experiment progressed. 520 days. That is 1.4 years. A generation ship traveling at the most optimistic speeds we can currently theorize for a crewed vessel would take thousands of years to reach even the nearest star. 520 days is roughly 20,000 days divided by 40. The psychological data from Mars 500 describes what happens in the first 1/40th of a single generation's voyage. Multiply what those 6 volunteers experienced across 20,000 days. Then multiply that across 15 generations of people who have never seen a horizon, never felt rain, never stood on ground that wasn't manufactured metal beneath their feet. Now here is the question. Nobody designing these missions wants to answer honestly. What gives the people born on that ship any obligation to continue? Those people never signed anything. They never volunteered. They were born into a mission conceived by ancestors they never met, aimed at a destination they have never seen, for reasons that may feel increasingly abstract as centuries pass. The original crew believed in the mission passionately enough to board the ship and leave everything behind. Their great-great-great-grandchildren, raised in the same recycled air, eating the same synthesized food, staring at the same metal walls. Their entire lives, what mechanism ensures those people maintain the same commitment? What governance structure holds 15 generations together without fracture? Think about what we know from isolated communities on Earth. Small islands with limited contact with the outside world. Monasteries, long-term prison populations, isolated religious communes. Every anthropological study of communities cut off from broader society shows predictable patterns: internal power struggles, ideological drift, factional violence, and eventual fragmentation or collapse. These communities had the ground beneath them. They had sunlight. They had the possibility of escape. Remove all of those and lock 10,000 people into a sealed vessel for 1,000 years, and the social dynamics do not become more stable. They become less. Quick question. Do you think the 10th generation aboard that ship would still care about the destination planet? Imagine being locked inside a large apartment building with 10,000 people. No internet, no windows, no access to the outside world, no nature, no weather, no horizon of any kind. Your children will live there. Their children will live there. 15 generations of your descendants, all born inside the same walls, breathing the same air, never once leaving. How many of those generations stay unified around a goal set by people who died 1,200 years before they were born? We cannot maintain civil behavior on a 14-hour flight from New York to Tokyo. Passengers argue over reclined seats. Flight attendants manage conflicts over carry-on luggage. We find 14 hours in an aluminum tube genuinely trying. And yet the generation ship concept asks us to believe that 15 generations of human beings, each one born without choice into confinement, each one carrying all the psychological complexity and social friction that defines our species, will maintain cohesion, purpose, and institutional memory across a journey lasting longer than the entire span of recorded human civilization. That is not pessimism. That is pattern recognition. The generation ship is not a grand epic waiting to be written. It is a sociological disaster unfolding in slow motion, across centuries, in a box with no exits. The biology fails, the psychology fails, the social structure fails, and all of this happens before a single mechanical component breaks down, which brings us to the next problem. Because the physics hasn't even started sending its bill yet. And if somehow the ship survives intact across thousands of years, physics will present its energy invoice. And that number will make the entire GDP of Earth look like loose change. To go far, you need to go fast. To go fast, you need to accelerate. Simple logic. The kind of reasoning that feels almost too obvious to state out loud, the same logic that got us from horse-drawn carriages to jet engines to orbital rockets in the span of roughly 2 centuries. We identified the problem. We built better engines. We went faster. The pattern worked every time before. Then you do the math for interstellar travel, and the pattern shatters. To accelerate a crewed spacecraft of 1,000 metric tons, a vessel modest by any serious interstellar standard, the absolute minimum you might consider for keeping a crew alive across a long voyage to 10% of the speed of light, and then decelerate it completely upon arrival. The energy required is equivalent to the entire electrical output of Earth running continuously for tens of thousands of years. Not a year, not a decade, tens of thousands of years of every power plant on the planet operating at full capacity. Every kilowatt hour produced across that entire span, devoted entirely to moving one ship one way between 2 star systems. That is the energy bill for 10% of the speed of light. The kind of speed that still takes 42 years to cover the distance to Alpha Centauri. Now, consider the comfortable option, accelerating at 1g, the same gravitational pull. You feel standing on Earth right now, the rate most compatible with long-term human health. A ship would need approximately 1 full year of continuous thrust just to approach near light speed. Then another full year of continuous deceleration to stop at the destination. 2 years of engines burning at maximum output, non-stop, just for the acceleration and braking phases alone, before accounting for the actual transit distance in between. And during every second of those 2 years, the fuel is being consumed at a rate that staggers any comparison to existing propulsion systems. There is no coasting option here, no energy-free glide phase. On Earth, a car rolling down a highway eventually slows from air resistance and road friction. An airplane cuts its engines and descends through atmosphere. Everything in our lived experience of motion involves passive deceleration. The environment does some of the work for you without being asked. In interstellar space, there is no environment, no atmosphere, no friction of any kind. A ship at 10% light speed in the void between stars will remain at 10% light speed indefinitely unless something actively pushes against it. Every change in velocity speeding up, slowing down, course correction demands energy. All of it. Every time. With no assistance from the surrounding medium. Because there is no surrounding medium, driving a highway with no brakes captures part of it. You must use the engine to both accelerate and decelerate, and you cannot afford to run out of fuel. But even that analogy undersells it, because at least the highway has air pushing back against the car. In interstellar space, the silence is total and the physics is merciless. This brings us to a problem that has haunted rocket engineering since Konstantin Tsiolkovsky first wrote it down in 1897 and that no amount of engineering creativity has ever escaped. The rocket equation. The relationship is simple and devastating the more fuel you carry. The heavier your vehicle becomes. The heavier your vehicle, the more fuel you need to accelerate it. The more fuel you add to cover that extra weight, the heavier it gets again. The cycle feeds on itself without limit, each solution generating a larger version of the original problem. Here is a number that makes this concrete. What percentage of Saturn V's total mass at launch do you think was actually fuel? Approximately 94%. 94% fuel. 6% everything else: structure, engines, guidance systems, the capsule, the astronauts, every piece of equipment those astronauts needed for a mission to the moon and back. The most powerful rocket ever built was, in its most honest description, a carefully engineered fuel tank with a small habitable compartment bolted to the top. 6% of the total mass did everything that mattered. 94% existed solely to lift and burn itself. That ratio describes a journey to the moon. A journey to Alpha Centauri requires speeds millions of times greater. Apply the Tsiolkovsky equation to those numbers, and the fuel fraction approaches 100% so completely that no room remains for the ship itself, let alone any crew. The math doesn't produce an impractical answer. It produces an impossible one. Modern rockets are fundamentally enormous fuel tanks with a seat attached at the top. We have refined that concept into extraordinary precision over 70 years of aerospace engineering. But the underlying architecture, the essential nature of the machine, has not changed since Goddard's first liquid-fueled launch in 1926. And we are attempting to use that architecture, or something derived from it, to cross the distance between stars. Einstein would probably not be raising an eyebrow at this point. He would simply be pointing at the equation he wrote in 1905 and waiting quietly for us to read it more carefully. So the engines we have are inadequate by a margin too vast to bridge with refinement. What we need is not a better rocket. We need fuel so energy dense that the Tsiolkovsky trap stops closing in on itself. Fuel that carries more power per kilogram than anything chemistry or conventional physics can provide. And this is exactly where the universe plays its most vicious joke on every engineer who has ever tried to solve this problem. Chemical propellant is how we reach space today. Liquid hydrogen combined with liquid oxygen, ignited in a controlled burn that produces the thrust necessary to escape Earth's gravity. It is the same fundamental chemistry that powered the Saturn V, the space shuttle, and every significant crewed launch in history. We have refined it across 7 decades into something genuinely impressive. Precise, reliable, energy-dense by the standards of anything you might put in a car or a jet. The energy density of the best chemical propellants sits at approximately 10 megajoules per kilogram. 10 megajoules per kilogram gets you to orbit, it gets you to the moon, it gets you, with considerable architectural cleverness, to Mars and back in theory. For those destinations, chemical propulsion is adequate, if brutally inefficient. For interstellar travel, 10 megajoules per kilogram is not inadequate. It is not underpowered. It is simply irrelevant, a number so far below what the problem requires that improving it by 10 times, or 100 times, or 1,000 times within the chemical framework still leaves you nowhere near the threshold. The gap between chemical fuel and interstellar travel is not a gap you close with better chemistry. It is a gap between categories. So the next step up is nuclear. Fission reactors splitting heavy atoms release energy at densities millions of times greater than chemical combustion. Nuclear pulse propulsion concepts, like Project Orion, studied seriously by the United States in the late 1950s and early 1960s, proposed detonating nuclear bombs behind a spacecraft to push it forward. The energy density is real. The physics works. And even Project Orion's most optimistic projections produced speeds that would still require thousands of years to reach Alpha Centauri. Fusion is the more elegant option. fusing light atoms rather than splitting heavy ones, the same process powering the sun. The energy density is higher, the waste products are cleaner, and the fuel, primarily hydrogen isotopes, is theoretically abundant. There is only one problem. We have been trying to build a stable, sustained fusion reactor for 70 years. The International Thermonuclear Experimental Reactor, ITER, currently under construction in southern France at a cost exceeding $20 billion, is designed to demonstrate that fusion can produce more energy than it consumes. It is not a power plant. It is a proof of concept. It has been under construction since 2013 and is not expected to achieve full fusion experiments until the early 2030s. After 70 years of research and billions in investment, controlled fusion remains perpetually on the horizon. But even if fusion were solved tomorrow, the shielding problem alone threatens to make it unworkable for interstellar vessels. A nuclear reactor operating at the energy levels required for interstellar propulsion produces radiation intense enough to kill the crew many times over. The shielding required to protect human beings from that radiation weighs hundreds of metric tons. Add hundreds of tons of shielding to the ship, and the Tsiolkovsky trap from the previous problem snaps shut again immediately. More mass means more fuel. More fuel means more mass. The cycle restarts with a larger and more catastrophic version of the same arithmetic. Then there is antimatter. Theoretically, it is the perfect fuel. When a particle of matter meets its antimatter equivalent, both annihilate completely. Converting 100% of their mass directly into energy, Einstein's equation works in both directions, and in the annihilation direction. It is absolute. 1 gram of antimatter meeting 1 gram of matter releases energy equivalent to the atomic bomb dropped on Hiroshima in 1945. The energy density is not millions of times better than chemical fuel. It is billions of times better. On paper, antimatter is the only fuel that could make interstellar travel energetically conceivable. Now for what the universe has to say about that. The total amount of antimatter humanity has ever produced across all particle accelerators in all countries, across all decades of research, is less than 20 nanograms. 20 nanograms. A nanogram is 1/billionth of a gram. 20 nanograms is an amount so small it is invisible to the naked eye, detectable only with sensitive instruments. CERN, the most sophisticated particle physics facility ever built, produces antihydrogen atoms in quantities measured in the thousands per experimental run, and those atoms survive for fractions of a second before annihilating. The estimated cost of producing 1 gram of antimatter using current technology runs to approximately $25 million trillion. That figure is not a typo. $25 million trillion, a number more than 200 times larger than the entire gross domestic product of every country on Earth combined in a single year. And a crewed interstellar mission would require not 1 gram, but many kilograms, possibly metric tons of antimatter to function. Using antimatter as interstellar fuel is like making a loaf of bread entirely from solid gold. The recipe works. The physics doesn't prohibit it, but the entire economic output of human civilization across recorded history couldn't pay for 1 slice. And that is before addressing storage. Antimatter cannot touch ordinary matter. Any contact produces immediate annihilation. Storing it requires magnetic containment traps that must operate continuously without interruption. No power fluctuation, no equipment failure, no interruption of any kind, ever, for the entire duration of a journey lasting potentially thousands of years. A power outage lasting 1 second, anywhere in the containment system, triggers an explosion proportional to the amount of antimatter stored. A ship carrying kilograms of antimatter that loses containment doesn't malfunction. It ceases to exist. So how long do you think it would take? Using CERN's current production rate to manufacture enough antimatter for a single interstellar mission. The answer, working from current production figures, is on the order of billions of years, longer than the current age of the Earth. The production problem alone, independent of cost, independent of storage, independent of every other obstacle in this story, places antimatter propulsion outside the reach of any civilization operating within a finite time frame. Engineers who design interstellar ships around antimatter propulsion are essentially retirement planners whose entire financial strategy depends on winning Powerball. Theoretically sound, mathematically coherent, not something you should quit your day job over. The fuel ladder runs from chemical to fission to fusion to antimatter, and every rung either exceeds our engineering ability, bankrupts our civilization in theory, or requires us to solve problems that have resisted solution for generations. Every option that provides enough energy density to matter comes packaged with a set of requirements that cannot currently be met, and in some cases, may never be met. Assume, for the sake of argument, that we solve it anyway. Assume some breakthrough materializes. The ship gets its fuel, the engines fire, and it leaves the solar system on a heading for another star. The fuel problem is behind us. The silent sky ahead has already started killing the crew in ways no one can see, and no armor has ever stopped. The International Space Station is the most sophisticated closed-loop life support system human beings have ever constructed. It took over a decade to assemble, involved 16 nations, cost approximately $150 billion, and represents the absolute cutting edge of our ability to keep people alive in space. Astronauts have lived aboard it continuously since November of 2000. It is the gold standard, the single best answer humanity has ever produced to the question of how you sustain human life away from Earth. The water recycling system aboard the ISS recovers approximately 90 to 93% of the water used by the crew. Urine, sweat, moisture from exhaled breath, all of it is captured, processed, and returned as potable water. By any terrestrial standard, this is a remarkable achievement. 90 to 93% recovery is extraordinary engineering. It also means 7 to 10% of the water is lost every cycle, irretrievably, gone into surfaces, into imperfect seals, into entropy. On the ISS, that loss is not a problem because resupply missions arrive regularly. Lost water gets replaced. The system doesn't need to be perfect because the Earth is always there as a backup. On an interstellar voyage, there is no resupply. The 7 to 10% lost compounds, every cycle, the total water inventory shrinks. Every year, the margin for error narrows. Over a journey of 100 years, a short interstellar voyage by any serious estimate, the cumulative loss becomes existential. And water's only one of dozens of consumables cycling through a closed life support system. Atmosphere, food precursors, chemical reagents for recycling processes. Biological cultures in life support loops, each one subject to the same inexorable attrition. This is not a design flaw that better engineering eliminates. It is the second law of thermodynamics, and it does not negotiate. Entropy always increases in a closed system. Always. Every physical process generates some waste, some degradation, some irreversible loss of usable energy and ordered structure. A life support system operating for 1,000 years is not a machine running for 1,000 years. It is a machine fighting entropy for 1,000 years. And entropy has never lost that fight over any time scale long enough to matter. The ISS gets resupplied. The interstellar ship does not. The difference between those two situations is the difference between a battle you can sustain and one you cannot. Then there is the hardware itself. Every component aboard a spacecraft has what engineers call a mean time between failures. The average operational lifespan before that component requires repair or replacement. The best engineered components in the most demanding aerospace applications have mean times between failures measured in years. sometimes decades. These are genuinely impressive numbers, won through careful design and rigorous quality control. A ship carrying millions of individual components, pumps, valves, seals, sensors, processors, filters, structural fasteners, thermal regulation systems, electrical connections across a voyage lasting thousands of years, produces a failure probability that converges on certainty. Not near certainty, not very high probability, mathematical certainty. At some point during a sufficiently long voyage, every component fails. The question is only whether the failure happens before or after a replacement can be fabricated or a redundant system takes over. Redundancy is the standard engineering answer to this problem. Build 2 of everything critical. Build 3. Design systems that automatically switch to backups when primary components fail. This works. It is why commercial aircraft are extraordinarily safe, despite consisting of thousands of moving parts. Redundancy saves lives and extends operational lifetimes dramatically. But on an interstellar vessel, redundancy carries a compounding cost. Every backup system adds mass. More mass means more fuel, which triggers the Tsiolkovsky equation again. Every additional layer of complexity introduces new failure modes. The backup systems themselves can fail, and their failure modes interact with primary systems in ways that are difficult to predict across decades. A redundant system that saves the mission on year 40 might introduce a subtle vulnerability that manifests catastrophically on year 200. The more complex the machine, the larger the space of possible failure combinations becomes, and across thousands of years, that space becomes effectively infinite. What component on the ISS do you think fails most frequently? The answer, perhaps unsurprisingly, is the toilet. The waste management system officially. The waste and hygiene compartment has required repair, replacement, and emergency intervention more times than any other single system on the station. NASA has devoted more engineering hours, more meetings, and more contingency planning to human waste management in microgravity than to almost any other operational challenge. This is not a criticism of NASA. It is a reflection of how relentlessly the physical world resists the desire for things to work cleanly and simply when human biology is involved. Driving an old car across a desert with no gas stations and no mechanics captures a fraction of the problem. Just you, a toolbox, and the hope that the air conditioning holds through the hottest week of summer. The interstellar version of that drive lasts 1,000 years. The desert has no edges. And if the engine fails on day 10,000, the nearest mechanic is 4 light years away and cannot be reached before everyone aboard is long dead. NASA has spent more time in meetings discussing the sanitation and waste recycling challenges of human spaceflight than it has conducting actual launches. The reality of long-duration space habitation is not the clean, luminous corridors of science fiction. It is a constant, grinding, unglamorous war against mechanical decay, biological waste, and the second law of thermodynamics fought with spare parts, improvised repairs, and careful rationing, with Earth always available as a final backstop. Remove that backstop, and the war becomes unwinnable by definition. The ship can be perfect on launch day. It cannot be perfect on year 500. Physics won't allow it. But even a perfect ship, every system functioning, every component holding cannot protect the people inside it from what the universe is continuously doing to them from the outside. Something invisible, something that passes through walls as if they don't exist, something that no amount of mechanical redundancy addresses. Because it isn't attacking the machine. It's attacking the crew directly, at the cellular level, and it has been doing so since the moment the ship left the solar system's magnetic embrace. On Earth, you live inside 2 overlapping shields that you have never once had to think about. The first is the magnetosphere, a vast magnetic field generated by the churning iron core of the planet, extending tens of thousands of kilometers into space. deflecting the continuous stream of charged particles the sun throws at us around the clock. The second is the atmosphere, a column of air roughly 100 kilometers thick, pressing down on every square centimeter of your body, absorbing and scattering the radiation that slips past the magnetic field. Together, these two layers reduce your annual radiation exposure to roughly 3 millisieverts per year. You were born inside them. You have never spent a single day without them. They are so constant, so complete, that the human body never developed any mechanism to detect radiation at all. Because for the entire history of our species, the planet handled it automatically. Step outside them, and the numbers change immediately and dramatically. Aboard the International Space Station, which orbits at roughly 400 kilometers altitude and still benefits from partial magnetic protection, astronauts absorb between 150 and 200 millisieverts of radiation per year. That is 50 to 60 times the dose received at sea level. A 6-month mission on the ISS exposes a crew member to the equivalent of 15 to 25 years of ground-level radiation compressed into half a year. NASA tracks cumulative career dose limits for its astronauts carefully. The agency sets a lifetime occupational limit of approximately 600 millisieverts, a threshold calculated to keep excess cancer risk below a defined ceiling across an astronaut's entire career. A one-way trip to Mars, lasting 8 to 9 months, delivers approximately 300 millisieverts. Half a career limit. One way, before the astronaut has set foot on the surface, half their lifetime professional radiation budget is already spent just getting there. Now extend that voyage not to Mars, but to another star. Not 8 months, not 8 years, decades, centuries, generations. The source of the problem is galactic cosmic rays, GCR. High-energy particles accelerated to near light speed by supernova explosions across the galaxy, streaming through interstellar space in every direction continuously. Unlike solar radiation, which varies with the sun's activity cycle and can be partially anticipated, galactic cosmic rays arrive constantly from all directions at energy so extreme they pass through most ordinary shielding materials as though those materials were not there. Lead stops lower energy radiation effectively. Against galactic cosmic rays, lead does something worse than fail when a high-energy particle strikes a dense material like lead. It triggers a cascade of secondary particles, pions and neutrons, that spray through the shielding and into whatever is behind it. The shield makes the radiation environment worse, not better. This phenomenon, called secondary radiation production, means that the intuitive solution build thicker walls actively increases the danger to the crew at high energies. Water shields better than lead for this reason. Hydrogen-rich materials absorb and scatter galactic cosmic rays more effectively without producing the same catastrophic secondary cascades. But the quantity of water required to provide meaningful protection is not a few centimeters. Meaningful shielding against galactic cosmic rays requires several meters of water surrounding the entire habitable volume of the ship. Apply that to a vessel large enough to sustain a crew across a generational voyage, and the mass penalty is not measured in tons, but in thousands of tons of water wrapped around the hull, which triggers the Tsiolkovsky equation with full force, demanding more fuel to move more mass, demanding more mass to carry that fuel, the spiral tightening again until the numbers become unworkable. On an interstellar voyage lasting centuries, the cumulative radiation dose received by crew members, even with the best shielding currently conceivable, guarantees outcomes that are not risks to be managed, but certainties to be acknowledged. Elevated cancer rates, accelerating cataract formation, measurable cognitive decline as high-energy particles damage neural tissue over years and decades. DNA strand breaks accumulating faster than cellular repair mechanisms can address them, damage that compounds across generations if the voyage is long enough to involve reproduction. the children born on that ship inherit not just the mission, but the biological consequences of the radiation environment their parents survived. Quick question. What do you think Earth's magnetic field is actually doing for you right now, in this moment, that you have never once noticed? It is deflecting a continuous stream of charged particles from the sun that, without that field, would strip away the atmosphere over geological time and bombard the surface with radiation levels incompatible with the biology that evolved here. Mars lost its magnetic field billions of years ago. Its atmosphere thinned to less than 1% of Earth's density. Its surface is now bathed in radiation that makes long-term human habitation without heavy shielding essentially impossible. Earth's magnetic field is not a feature of the planet. It is the reason complex life exists on it at all. Outside the solar system, traveling through interstellar space, there is no planetary magnetic field. There is no stellar wind from a nearby star creating a protective bubble. There is only the galaxy, and the galaxy is full of the energetic debris of dead stars moving in every direction at nearly the speed of light. Physicists designing radiation shields for interstellar vessels are solving a problem where every solution generates three new problems. The shielding adds mass, which requires fuel. Which adds mass, which requires more shielding to protect the fuel systems. Each answer feeding back into the original constraint in a loop with no clean exit. It is whack-a-mole, except the mallet is also trying to hit you, and the table is moving, and every mole you knock down splits into two smaller moles before it goes under. The radiation is invisible. It produces no sound, no heat, no sensation of any kind as it passes through the hull and through the bodies of the crew. No alarm sounds when a galactic cosmic ray nucleates a DNA strand break in a crew member's brain. The damage accumulates silently across years and decades, manifesting as illness long after the source events that caused it. You cannot fight what you cannot detect, and the human body has no detector for this at all. Radiation is invisible, but the next threat is very real, very solid, and moves fast enough to tear a ship apart before any radar in existence could register it. Space is empty. This is one of the foundational images we carry: the vast, clean void between stars, a near-perfect vacuum stretching across unimaginable distances. And compared to anything on Earth, that description is accurate. Interstellar space contains far fewer particles per cubic meter than the best vacuum chambers we can build in any laboratory. But empty by cosmic standards still means thousands of dust particles and microscopic meteoroids per cubic kilometer, distributed thinly across light years. Yes, present everywhere. Also yes. And at interstellar travel speeds, the distinction between a dust grain and a bomb collapses completely. At 10% of the speed of light, 30,000 kilometers per second, the physics of collision transforms entirely. A dust particle, 1 millimeter in diameter, the kind that settles invisibly on a windowsill on a calm afternoon, strikes the hull of a ship with kinetic energy equivalent to a conventional TNT explosive. 1 millimeter, 1 gram of dust, 1 bomb. A pebble 1 centimeter across, the kind you might kick aside without noticing, while walking a gravel path carries impact energy at that velocity equivalent to a tactical nuclear weapon, not similar in scale. Equivalent, the same order of magnitude as the nuclear weapons deployed in warfare. Now consider the reaction time available. At 10% of the speed of light, an object 1,000 kilometers ahead of the ship, roughly the distance between New York City and Detroit, will impact in 1/100th of a second. 100th of a second from detection to collision, assuming a perfect detector operating with zero latency, which does not exist. The fastest radar systems ever built, the fastest computing systems ever designed, the fastest automated response mechanisms in any engineering application cannot process, decide, and execute an evasive maneuver in 1/100th of a second. Human reaction time is approximately 200 milliseconds, 20 times too slow. Even artificial intelligence operating at the limits of current hardware cannot bridge that gap at interstellar velocities. The object is simply there, and then the collision has already happened, before any system aboard the ship has had time to register the threat. The standard engineering response to impact threats is armor. Build the forward hull thick enough to absorb collisions. NASA has used Whipple shields on spacecraft for decades, a design that places a thin outer sacrificial layer spaced away from the main hull, so that incoming particles vaporize on the outer layer and the resulting debris cloud disperses before reaching the pressure hull. Whipple shields work effectively against objects smaller than roughly 1 centimeter at the orbital velocities typical of Earth-orbiting spacecraft a few kilometers per second. They are a genuine solution to a real problem within their design parameters. At interstellar speeds, the Whipple shield's design parameters become irrelevant. A particle hitting at 30,000 kilometers per second does not vaporize cleanly on a thin sacrificial layer. It generates a hypervelocity plasma jet that penetrates through multiple layers of material, and the secondary ejecta from the initial impact scatter inward with enough energy to cause catastrophic damage to systems behind the shield. The armor itself becomes part of the projectile. A thicker shield helps until the mass penalty triggers the Tsiolkovsky cascade again, and the additional shielding mass demands additional fuel. Mass demands additional structural mass, the familiar spiral tightening with every ton added to the forward hull. Quick question: how many times do you think the ISS gets struck by micrometeoroids and space debris every single day? The answer is dozens to hundreds of times daily. Impacts are so frequent that the ISS hull has accumulated thousands of small craters and pits across its external surfaces over its operational lifetime. Engineers inspect and patch regularly. The ISS survives this constant bombardment because orbital velocities roughly 7 to 8 kilometers per second are low enough that the Whipple shield and hull armor handle the impacts without catastrophic failure. Scale the velocity up from 8 kilometers per second to 30,000 kilometers per second, a factor of nearly 4,000, and the energy of each impact scales with velocity. Squared, meaning energy increases by a factor of approximately 16 million for the same particle mass. Every dust grain that was harmless at orbital speed becomes a lethal projectile. Flying at interstellar velocity through interstellar space is like driving 300,000 kilometers per hour through a pitch-black night with no headlights, where the things you hit look like dust but explode like bombs, and you will never see any of them coming. The engineering proposals to address this are instructive in their ambition and their cost. One serious suggestion involves generating a plasma cloud ahead of the ship. Superheated ionized gas projected forward that vaporizes incoming particles before they strike the hull. Theoretically functional. The energy required to maintain that plasma cloud continuously across an interstellar voyage equals the continuous output of several nuclear power plants, just for the shield, just to vaporize the dust. On top of everything else, the ship needs to power. The ISS gets hit hundreds of times a day and survives because it moves slowly. An interstellar ship would need to move fast enough to make the journey conceivable within any reasonable time frame, and that speed is precisely what turns every grain of interstellar dust into a potential mission-ending event. And if somehow you survive all of this, the radiation, the impacts, the mechanical decay, the social collapse, the fuel impossibility Einstein is waiting for you in what comes next, with a story about time that will make you never want to come home again. Einstein's special theory of relativity contains a prediction so counterintuitive that even physicists, when they first encounter it, spend time sitting quietly with the discomfort before accepting it. The faster you move through space, the slower you move through time. Not metaphorically, not as a perceptual illusion. Physically, measurably, absolutely time itself passes at a different rate for an object in motion than for an object at rest. The faster the motion, the greater the divergence. This is called time dilation, and it sounds, on first hearing, like the most exciting feature of interstellar travel imaginable. It is, in reality, the cruelest one. The numbers are precise, and they have been verified. At 90% of the speed of light, every 1 year experienced aboard the ship corresponds to 2.3 years passing on Earth. Already the gap is significant. A 10-year voyage at that speed means more than 23 years have elapsed at home before you return. At 99% of the speed of light, the ratio steepens sharply. 1 year on the ship equals 7 years on Earth. A 10-year mission at that velocity returns you to a world where 70 years have passed. Everyone who was middle-aged when you left is dead. Children you knew are elderly. The world has reorganized itself around your absence without noticing. At 99.9% of the speed of light, 1 year aboard equals 22 years on Earth. These are not approximations. They come directly from the relativistic Lorentz factor, the mathematical relationship Einstein derived in 1905 that describes exactly how time, length, and mass transform at high velocities. The equations are among the most thoroughly tested in all of physics. Every particle accelerator on Earth confirms them daily. Every GPS satellite in orbit requires relativistic corrections to maintain accuracy, because the satellites move fast enough that their onboard clocks drift measurably from ground-based clocks without adjustment. Remove those corrections, and GPS systems would accumulate positioning errors of several kilometers per day. And if you want to feel what the numbers mean at genuinely interstellar scales, consider the galactic center. The center of the Milky Way lies approximately 26,000 light-years from Earth. A ship accelerating at 1 g toward the galactic center, then decelerating at 1 g for the second half of the journey, would allow the crew to arrive having experienced approximately 20 years of personal time, a manageable human lifetime. A journey one person could complete from youth to middle age. The physics permits this. When that ship turned around and made the return journey, arriving back at Earth after another 20 years of personal time, the crew would step off the ship to find that 52,000 years had passed on Earth. 52,000 years. The last Neanderthals walked the Earth 50,000 years ago. The entirety of recorded human civilization, every dynasty, every empire, every war, every scientific revolution, every piece of art ever created fits inside a window of roughly 5,000 years. The returning crew would arrive in an Earth that is more distant from the one they left than we are from the people who first painted on cave walls in France and Spain. This is not science fiction. This is verified physics. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial aircraft and compared them to reference clocks that remained on the ground. The airborne clocks, moving faster than the ground clocks, ran slightly slow relative to the stationary ones, exactly as special relativity predicted. The discrepancy was measured in nanoseconds because aircraft travel at a tiny fraction of light speed, but the effect was real, measurable, and matched the theoretical prediction with precision. The same mechanism that shifted those atomic clocks by nanoseconds on a transatlantic flight shifts human biology by decades and centuries at interstellar velocities. This reframes what interstellar travel actually is in human terms. It is not simply going somewhere distant. It is permanent exile from your own civilization in time, not just space. You do not merely leave Earth behind in physical location. You leave it behind in history. Every year you spend aboard the ship, every year you survive the radiation and the mechanical failures and the social pressures and the fuel constraints to actually approach another star. The world you came from recedes not just in distance, but in time. You cannot phone home and catch up. You cannot return and pick up where you left off. The home you left does not exist in the form you left it. The people you knew are gone. The institutions, the languages, the cultural references, the political structures, everything that constituted the civilization you belonged to has continued without you for centuries or millennia. Quick question, and take a moment with this one. If you could travel at near light speed and experience only 10 years personally, but when you returned to Earth, 500 years had passed, would you go? Think about what that means concretely. You are 30 years old when you leave. You return, biologically 40, to an Earth where 530 years have elapsed since your departure. Everyone you have ever known, loved, argued with, grown up alongside all of them are gone, along with their children and grandchildren and great-grandchildren, all the way down. The language may have drifted beyond recognition. The country you called home may not exist as a political entity. The scientific knowledge you carried with you when you departed may be 500 years obsolete. You return not as a traveler coming home, but as a relic from a vanished era, carrying memories of a world that everyone alive regards as ancient history. Interstellar travel is, functionally, the only anti-aging program that actually works. You stay biologically young while time accelerates outside the ship. The universe grants you extra decades by slowing your clock, relative to the rest of reality. The price is that everyone you love turns to dust while you are getting younger. There is something almost unbearable in that exchange, the universe offering you the stars, and the fine print requiring you to trade away everyone and everything that made the stars worth seeing in the first place. The practical consequence is stark. Any civilization that sends people to other stars is not sending explorers who will return with reports. It is sending people into permanent temporal exile. The crew that departs is not the crew that arrives, and even if they somehow make it back, they return to a world that has no use for the information they carry because everything has changed around it. The mission is a one-way door, not just through space, but through time, and unlike the physical distance, the temporal separation cannot be reversed by any known mechanism in physics. The universe is not punishing ambition. It is simply structured in such a way that speed and time are entangled at the most fundamental level, and the price of covering interstellar distance at any velocity worth discussing is paid in the currency of human connection, human belonging, and human continuity. You leave. The clock runs differently. You cannot come back to what you left. Not really. Not ever. All right, suppose you accept all of it. Every cost, every separation. You reach another star. You find a planet. You land. And this is when the universe delivers its final, cruelest move. Proxima Centauri b. The name carries weight in astronomy circles, the closest known exoplanet to Earth, orbiting within the habitable zone of our nearest stellar neighbor, sitting at a distance of just 4.24 light-years. When its discovery was confirmed in 2016, headlines around the world used words like promising, potentially habitable, and Earth-like neighbor. For a brief moment, the destination problem seemed almost solved. We knew where to go. We had a candidate. The closest star had a planet in the right zone. Then the astronomers started reading the fine print, and the fine print was devastating. Proxima Centauri b is tidally locked to its star. This means the planet does not rotate relative to its sun the way Earth rotates relative to ours. One hemisphere permanently faces Proxima Centauri, bathed in continuous stellar radiation, heated to temperatures that make any Earth-like surface chemistry impossible. The other hemisphere permanently faces away, frozen in perpetual darkness at temperatures hundreds of degrees below zero. There is no day-night cycle, no seasonal rhythm, no global circulation pattern that distributes heat the way Earth's atmosphere moderates temperature across latitudes. The Terminator line, the narrow band between the scorched day side and the frozen night side, might theoretically support some narrow habitable corridor, But that depends entirely on whether the planet has a substantial atmosphere. And the evidence on that question points in the wrong direction entirely. Proxima Centauri itself is the deeper problem. It is a red dwarf star and not a quiet one. Red dwarfs are the most common type of star in the galaxy, and they are also, in their early billions of years, extraordinarily violent. Proxima Centauri is classified as a flare star, meaning it periodically releases massive bursts of ultraviolet radiation and X-rays orders of magnitude more intense than anything our sun produces. In 2019, astronomers documented a flare from Proxima Centauri that briefly made the star approximately 1,000 times brighter in ultraviolet wavelengths than its baseline output. 1,000 times, a single event of that magnitude, striking a planet with no magnetic field and no substantial ozone layer, would strip the surface of any protective atmospheric chemistry and deliver a radiation dose sufficient to sterilize exposed biology entirely. There is no confirmed evidence that Proxima b has a magnetic field. There is no confirmed evidence of a thick protective atmosphere. Without both, the surface of that planet during a major flare event is not a place where life struggles. It is a place where complex chemistry ceases to function on timescales of minutes. Here is a question worth sitting with. Out of the approximately 5,600 exoplanets confirmed as of 2024, how many do you think have conditions where a human being could breathe the air without a pressurized suit and oxygen supply? 0. Not approximately 0. Exactly 0. Not one confirmed exoplanet in the entire catalog of discovered worlds has been verified to have breathable atmosphere, survivable surface pressure, tolerable radiation environment, and liquid water simultaneously accessible at the surface. Every exoplanet we have found either orbits too close to its star, too far, lacks atmosphere, has the wrong atmospheric composition, receives too much radiation, or remains too poorly characterized to assess. The galaxy contains hundreds of billions of planets. We have confirmed over 5,600 of them. The number with confirmed human habitable conditions is 0. Science fiction has spent decades painting exoplanets as lush green worlds, waiting to receive us oceans gleaming under alien suns, breathable skies, soil that grows food. The actual catalog of exoplanet astronomies presents a very different picture. Most confirmed planets are gas giants or super-Earths with crushing surface pressures. The rocky ones in habitable zones tend to orbit red dwarfs that periodically irradiate them with lethal intensity. The ones that look most promising from a distance reveal serious disqualifying conditions on closer examination. Real exoplanets look far less like paradise and far more like various categories of hostile environment, and at least actual hell doesn't bombard your DNA with ionizing ultraviolet every few months. But suppose, against all evidence, that there is a planet out there that works. Survivable atmosphere, tolerable radiation, liquid water, stable star. Suppose the crew reaches it after centuries of travel, survives the landing, establishes a foothold, and then something goes wrong. A medical emergency no one on the ship can treat. A structural failure that requires parts no one can fabricate. A biological threat, a pathogen, a toxic compound in the local environment, an allergic response to something in the air that shuts down the immune system of half the crew. The signal takes 4.24 years to reach Earth at the speed of light. Earth's response, if Earth still exists in recognizable form after the temporal dilation effects of the voyage, if humanity still has the technological capacity to help, if the original mission is even remembered in institutional memory, takes another 4.24 years to return. 8.48 years of silence, while whatever went wrong continues going wrong without interruption, without any possibility of outside intervention. By the time any help could theoretically respond, the emergency that triggered the distress call is resolved one way or another, almost certainly the wrong way. There are no medevac flights from Earth to Alpha Centauri, There is no supply drop. There is no rescue mission that could be assembled, launched, and arrive in time to matter. The crew is not isolated the way Antarctic researchers are isolated, or the way sailors on a long ocean crossing are isolated, where isolation is temporary and rescue is theoretically possible, given enough time and resources. The crew is isolated the way no human beings in history have ever been isolated beyond any reach, beyond any help, beyond any connection to the civilization that sent them, with light-speed communication as the only thread remaining, and even that thread carrying only words, arriving years late from people who cannot do anything across that distance except listen and grieve. Settling on a hostile exoplanet with no rescue capability is like moving onto the slope of an active volcano during a radiation storm, with no hospital within reach, no phone signal, no emergency services, and no exit. On a bad day, you are simply gone, and the news of your death takes 4 years to reach anyone who cared about you. But perhaps none of this matters if we simply build better technology, faster engines, exotic propulsion, the kinds of drives that science fiction has promised for generations: warp speed, wormholes, shortcuts through space-time that render distance irrelevant. Perhaps physics has a loophole we haven't found yet. Perhaps the universe is not as closed as the previous 10 problems suggest. Sorry, this is where physics itself takes the floor. Warp drive. The words conjure a specific image immediately: the Starship Enterprise stretching into a streak of light, stars blurring into lines, the ship arriving at its destination in minutes rather than millennia. Wormholes conjure a tunnel through folded space-time, a shortcut that sidesteps distance entirely, the kind of thing that makes interstellar travel not a generational commitment, but an afternoon trip. These concepts are so deeply embedded in science fiction that they feel like promissory notes from physics, ideas the universe is holding in reserve until our engineering catches up. The actual status of both in physics is considerably less encouraging. The Alcubierre drive was proposed in 1994 by Mexican physicist Miguel Alcubierre as a mathematical exercise in general relativity. Alcubierre showed that Einstein's field equations, which describe how space-time curves in the presence of mass and energy, do permit a solution in which a region of space-time contracts in front of a ship and expands behind it, effectively moving the ship without the ship itself accelerating through space. Within the bubble, the ship experiences no acceleration, no relativistic time dilation, no violation of the light speed limit. Outside observers would see it move faster than light. The mathematics is internally consistent. The equations do not explicitly forbid it. The requirements for building one, however, are a different category of problem entirely. The Alcubierre drive requires exotic matter, a form of matter with negative energy density that does not correspond to anything observed in nature, not rare matter, not expensive matter, matter with a property. Negative energy density that has never been confirmed to exist as a stable, macroscopic substance anywhere in the observable universe. The Casimir effect demonstrates that quantum vacuum fluctuations can produce regions of slightly negative energy density at subatomic scales. But scaling this to the quantities needed for a warp bubble represents a jump of many dozens of orders of magnitude with no theoretical pathway connecting the two. In 2012, NASA physicist Harold White proposed a revised geometry for the Alcubierre metric that he claimed reduced the exotic matter requirement dramatically. The announcement generated significant media coverage. On examination, the revised design still required exotic matter with a mass-energy equivalent roughly comparable to a planet the size of Jupiter, and White himself subsequently stepped away from the research without producing a viable pathway forward. In 2021, physicist Eric Lentz published a paper proposing warp bubble configurations that might not require exotic matter at all. This also received enthusiastic headlines. The energy required to generate those configurations, on examination, exceeded the total mass energy content of the Sun. The entire Sun, converted completely to energy according to Einstein's equation, would not be sufficient to power a single warp transit. Additionally, any ship inside an Alcubierre bubble cannot send signals forward to navigate the bubble's structure, cuts off causal contact between the interior and the space ahead of it. The ship would be flying blind through whatever lay in its path, unable to steer, unable to brake, unable to respond to obstacles. Do you know what Alcubierre himself, the physicist who proposed the drive that bears his name, has said about its practical feasibility? He has described it consistently as a mathematical curiosity, a pure theoretical exercise exploring the geometry of general relativity, not an engineering proposal. The man who invented the warp drive on paper does not believe it can be built. He has said so directly, repeatedly, without ambiguity. Wormholes present a structurally similar story. The Einstein-Rosen bridge. A solution to Einstein's field equations connecting two separate regions of spacetime was described mathematically in 1935. It is a genuine feature of general relativity's geometry. It has also never been observed, and theoretical analysis of its properties consistently arrives at the same conclusion: traversable wormholes, the kind large enough to pass anything through, are catastrophically unstable without exotic matter to hold them open. Without that stabilization, a wormhole collapses in approximately 10 to the power of negative 43 seconds Planck time, the shortest meaningful unit of duration in physics. It closes before any signal, let alone any physical object, could traverse it. Recent work in quantum gravity, particularly the ER equals EPR conjecture connecting wormholes to quantum entanglement, suggests that microscopic wormholes may be a genuine feature of the quantum vacuum. But these structures exist at scales far below the atomic nucleus. Nothing passes through them. They connect quantum states, not locations. The gap between a subatomic quantum wormhole and a passage large enough for a spacecraft is not a technical gap to be bridged by engineering. It is a conceptual category difference with no known theoretical pathway between them. Designing an interstellar mission around warp drive is structurally identical to designing a national energy policy around Harry Potter's wand. Neither can be proven impossible by pure logic alone. Neither has ever been demonstrated in any controlled setting. Neither has a development pathway that connects current technology to operational capability. The difference is that physicists can point to the specific equations that explain why the warp drive fails, where the magic wand simply fails by absence of evidence. Both are equally unavailable as engineering solutions in any time frame that matters. So if no technology can bridge the distance, and no civilization in 6 decades of listening has ever sent us a signal suggesting any of them found a way around these constraints, either then, perhaps the barriers to interstellar travel are not a problem, unique to humanity's current developmental stage. Perhaps they are universal. Perhaps they are the answer to a question that has haunted astronomy since the 1950s. And if that is true, if the barriers to interstellar travel are not just our barriers, but everyone's barriers, written into the physics that governs every civilization in every corner of this galaxy, then what we have been calling an engineering problem might actually be something far larger. The answer to the greatest silence in the history of science. The Fermi paradox begins with a simple observation that becomes increasingly disturbing the longer you sit with it. The universe is approximately 13.8 billion years old. The Milky Way contains somewhere between 200 billion and 400 billion stars. At least 40% of those stars are estimated to host planets within their habitable zones. The numbers, by any reasonable calculation, suggest that life-bearing worlds should be common, and that civilizations with millions of years of technological development ahead of us should exist in enormous numbers throughout the galaxy. A civilization that emerged just 1 million years before us, a blink in cosmic time. Given that the universe is 13,800 times older, then that would have had sufficient time, at even modest rates of expansion, to colonize every star system in the Milky Way many times over. Not once, many times, even traveling at 1% of the speed of light. A civilization with a million-year head start could have saturated the entire galaxy before our ancestors learned to use stone tools. The math is not ambiguous on this point. And yet, silence. The search for extraterrestrial intelligence. SETI has been systematically scanning the sky for signals of artificial origin since 1960. 60 years of listening across radio frequencies, optical wavelengths, and increasingly sophisticated detection methodologies. Not one confirmed signal of deliberate, intelligent, extraterrestrial origin. Not one anomaly that survived rigorous scrutiny. The universe, on the question of other technological civilizations, has returned nothing but static. This is the Fermi paradox. The universe should be full of voices. We hear none. In 1998, economist Robin Hanson formalized a framework for thinking about this silence called the Great Filter. The argument is straightforward somewhere along the developmental path from chemistry to spacefaring civilization. There must be a barrier so difficult to cross that virtually no species crosses it. A filter, something that stops civilizations from becoming the kind of galaxy-spanning presence that would be detectable or capable of making contact. The question Hansen raised, and the question that has made physicists and philosophers deeply uncomfortable ever since, is where that filter sits in the sequence. If the Great Filter lies behind us, we are extraordinarily lucky. Perhaps the emergence of life from chemistry is near impossible. Perhaps the leap from single-celled to multicellular organisms almost never happens. Perhaps complex animal neurology capable of producing technology is a 1 in a trillion coincidence. If humanity has already passed through the filter, the silence makes sense. We are among the first to make it through, and the universe ahead of us is genuinely open. But there is another possibility, the one that sits in the back of the mind and refuses to leave quietly. What if the Great Filter lies ahead of us? What if the barrier is not something in our past that we were lucky to survive, but something in our future that no civilization, regardless of intelligence or technological sophistication, has ever successfully overcome? What if the physics of interstellar travel is not a problem, waiting for a smart enough solution, but a wall built from the structure of reality itself? One that applies identically to every civilization in every corner of every galaxy, without exception and without appeal. This possibility reframes the entire story, told across the previous 12 parts of this series. The vacuum, the distances, the speed limit, the fuel impossibility, the radiation, the mechanical entropy, the social collapse, the temporal exile. Every barrier examined in sequence, not as a list of human engineering failures, but as a universal curriculum that every civilization eventually encounters and that none have demonstrably passed. The silence of the universe is consistent with this interpretation in a way that is genuinely chilling. It is not necessarily the silence of an empty universe. It may be the silence of a full 1 billion of civilizations, each locked inside its own solar system by the same laws of physics that lock us inside ours, each looking up at the same night sky, each sending signals that travel at light speed and arrive too late or too faint to detect across the distances involved, each concluding, eventually, that they are alone, not because they are, but because the universe is structured so that meeting is impossible. Think about billions of people living on separate islands, scattered across an ocean so vast, no vessel can cross it. Each island has its own language, its own history, its own science. Each one looks up at the same stars. Each one wonders. None of them know the others exist, not because the others aren't there, but because the ocean between them has no crossing. The stars above are shared. The ground beneath never is. Here is a question worth sitting with genuinely, not rhetorically. Do you believe the great filter is already behind us, something we have survived? Or do you believe it still lies ahead, waiting? The answer to that question is arguably the most consequential belief a civilization can hold about itself. If the filter is behind us, expansion remains theoretically possible, and the universe is ours to explore given sufficient time. If the filter is ahead, then every civilization that has ever asked this question has asked it from inside the same cage we are standing in right now, and the cage has no door that physics permits us to open. We have spent 60 years listening to the universe and heard nothing deliberate in return. Perhaps the universe has been listening just as carefully and hearing the same thing from every direction. A party where no one can get to the venue because the bus doesn't go there and never has and never will, because the route passes through physics that does not accommodate the journey. But if we cannot go to the stars, does that mean we have failed? Or does it mean something deeper is waiting to be understood? Something that reframes what exploration actually means for a species living inside hard limits? In 1610, Galileo Galilei pointed a telescope. He had built himself an instrument with a lens roughly 3 centimeters in diameter, magnifying objects about 20 times at Jupiter, and saw 4 small points of light that moved from night to night in a way that could only be explained if they were orbiting the planet. Moons, other worlds circling another body, not Earth. The observation did not require Galileo to travel to Jupiter. It did not require him to leave Padua. It required him to look more carefully than anyone had looked before, with a slightly better instrument than anyone had previously constructed. That single act of patient observation from a fixed location on Earth overturned 2,000 years of cosmological assumption and permanently altered humanity's understanding of its place in the universe. Galileo never traveled to Jupiter. He never needed to. The knowledge came to him. The James Webb Space Telescope, launched in December of 2021 and positioned at the second Lagrange point, approximately 1.5 million kilometers from Earth, currently images galaxies that formed when the universe was only 300 million years old 13.4 billion years ago, when the cosmos was barely 2% of its current age. The light captured in those images left its source before our sun existed, before the solar system condensed from its protostellar cloud, before Earth formed, before the first single-celled organism appeared in the ancient ocean. Webb observes the universe's own infancy from a platform 4 times farther from Earth than the Moon. Without any human being traveling anywhere near those ancient galaxies or needing to, the solar system alone contains enough exploration to occupy human civilization for thousands of years without exhausting the possibilities. Mars holds geological records stretching back 4 billion years, a frozen archive of early planetary conditions that could answer fundamental questions about how rocky worlds evolve and whether life appeared there independently. The asteroid belt contains trillions of objects ranging from dust grains to dwarf planets, preserving pristine material from the solar system's formation 4.6 billion years ago. Europa, the ice-covered moon of Jupiter, harbors a liquid water ocean beneath its frozen surface, an ocean that may have existed for longer than complex life has existed on Earth, in contact with a rocky seafloor that geothermal heating keeps warm. The Hubble Space Telescope observed water vapor plumes venting from Europa's surface in 2013, suggesting that ocean material cycles to the surface periodically. If life exists anywhere else in our solar system, Europa is among the most compelling candidates. Titan, Saturn's largest moon, has a dense nitrogen atmosphere thicker than Earth's, and lakes of liquid methane pooling in its polar regions, an entirely different solvent chemistry, operating at temperatures near negative 179 degrees Celsius, presenting questions about the diversity of possible biochemistry that no existing theory fully answers. Enceladus, another of Saturn's moons, actively vents water vapor and ice particles from its south polar region in geysers that extend hundreds of kilometers into space, and the Cassini spacecraft, which flew through those plumes before its mission ended in 2017, detected complex organic molecules, including hydrogen cyanide, a compound central to many theories of prebiotic chemistry on early Earth. Beyond the solar system, gravitational wave observatories like LIGO have opened an entirely new sensory channel on the universe, detecting ripples in space-time produced by merging black holes and neutron stars billions of light years away. Events so energetic, they briefly emit more power than all the stars in the observable universe combined. Detected from Earth without sending anything anywhere, the Event Horizon Telescope, a planet-spanning array of radio observatories coordinated to function as a single instrument the diameter of Earth, produced the first direct image of a black hole's shadow in 2019. The supermassive black hole at the center of the galaxy, Messier 87, 55 million light-years away, imaged from Earth without approaching it by a single kilometer. Dark matter, dark energy, the structure of space-time at quantum scales. The deepest questions in physics are being pursued not by traveling to where the answers are, but by building better instruments, developing more sophisticated theory, and looking more carefully at the light that has been arriving all along. Do you know what the James Webb Space Telescope is observing and contributing to right now, in this current period of its operation? Among its active programs, characterizing the atmospheres of exoplanets by analyzing how starlight filters through their atmospheric layers during transit. Detecting molecular signatures that could, in principle, identify biosignatures in distant planetary atmospheres without sending anything there. Mapping the distribution of dark matter through gravitational lensing, resolving the structure of the earliest galaxies in unprecedented detail, answering questions about stellar formation that Hubble's resolution could not address. All of it from a point in space, 1.5 million kilometers from Earth. There is a philosophical posture worth naming directly. Limits are not the same as failures. Every physical object in the universe exists within constraints. A star cannot exceed certain masses without collapsing under its own gravity. A planet cannot maintain an atmosphere below certain size thresholds. An organism cannot survive outside certain temperature and pressure ranges. These are not shortcomings. They are definitions. They are the specific shape that a particular thing takes within the laws governing the universe it inhabits. A civilization's boundaries are not the measure of its inadequacy. They are the outline of what it actually is. The inability to reach the ocean floor with naked human lungs does not make the ocean unexplorable. Sonar maps the seafloor in more detail than any diver's eyes could cover in 1,000 lifetimes. Remotely operated vehicles retrieve samples from the deepest trenches. Water pressure data, chemical analysis, acoustic imaging. Biological samples brought to the surface. The ocean yields its knowledge through instruments, not through unaided human presence at the point of interest. The knowledge reaches us. We do not need to reach it first. Humanity has spent hundreds of billions of dollars across decades trying to figure out how to reach the stars, while the floor of Earth's own oceans remains less thoroughly mapped than the surface of the moon. There is something clarifying about that fact, not as a criticism of ambition, but as a recalibration of what exploration actually means. Exploration is not the act of physically standing somewhere new. It is the act of understanding something that was previously unknown. The instrument that achieves that understanding doesn't need legs. The universe is not withholding itself from us because we cannot cross interstellar distances. It has been sending light to our eyes since before we had eyes to receive it. It has been broadcasting its history, its physics, its structure, and possibly its biology in the form of photons, gravitational waves, and neutrinos for 13.8 billion years. We are not cut off from the cosmos. We are immersed in it. The question has never been whether the universe is accessible. It is whether we are paying sufficient attention to what it has already been saying. But before you settle into the idea that this is where the story ends with humanity finding peace inside the solar system, with telescopes as our true instruments of cosmic belonging, there is one final truth waiting. Something that even the most rigorous physicists rarely say out loud in plain language. A realization that doesn't close the question. It opens a door to something larger than everything that came before it. Every barrier in this story, the vacuum, the distances, the speed limit, the fuel, the radiation, the entropy, the social collapse, the temporal exile, the hostile planets, the broken physics of warp drives and wormholes, has been presented as a technical problem, an engineering challenge, a set of obstacles that humanity has not yet found a way around, and may never find a way around. That framing is accurate. The physics is real. The numbers are real. The conclusions are real. But across 14 parts, across every category of failure and impossibility, nobody stopped to ask the question, sitting quietly underneath all of it. If we could, should we, not as an ethical abstraction, as a genuine, concrete inquiry, suppose every problem described in this series were solved tomorrow. Suppose a propulsion breakthrough materialized that bypassed the Tsiolkovsky trap. Suppose shielding was developed that neutralized galactic cosmic rays without adding fatal mass. Suppose generation ships were somehow kept socially coherent across 15 generations, and a planet was found with breathable air and tolerable radiation and liquid water. Suppose all of it worked simultaneously, in combination. The question that remains is not whether we could go. It is whether we understand enough about what we would be traveling through to have any business traveling through it at all. Here is the physical reality that 14 parts of this story did not address. Because every prior discussion assumed we were dealing with a universe we at least basically understood. Approximately 96% of the universe is something we cannot identify, cannot detect directly, and cannot explain in any complete theoretical framework currently available to physics. Dark matter, the invisible substance that makes up roughly 27% of the universe's total mass energy content, was inferred from galactic rotation curves, gravitational lensing effects, and the large-scale structure of the cosmic web. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. And despite decades of dedicated detector experiments, underground laboratories, particle colliders, satellite observatories, not one dark matter particle has ever been directly detected. We know it must be there because of what it does. We have no idea what it is. Dark energy is stranger still. Comprising approximately 68% of the universe's total energy content, it is the name physicists give to whatever is driving the accelerating expansion of space itself, a property of the vacuum that pushes galaxies apart at an increasing rate and will, over timescales of tens of billions of years, push every galaxy outside our local group, beyond the observable horizon permanently. We do not know what dark energy is. We cannot measure it directly. We infer it from the fact that the universe's expansion is speeding up, when gravity alone would predict it should be slowing down. The label dark energy is, in the most honest reading, a placeholder for an admission of ignorance. Ordinary matter, every atom in every star in every galaxy, every planet, every ocean, every living cell, every human being, every spacecraft ever constructed, every instrument ever pointed at the sky constitutes 4.9% of the universe's total mass energy content. We are attempting to travel through a medium of which we understand less than 5%. It is like a fish deciding to swim out of the ocean, not understanding that 95% of what surrounds it is not water, not a different kind of water, not denser or shallower water. Something categorically different from water, operating under principles The fish has no sensory apparatus to detect and no conceptual framework to interpret. The fish's entire model of reality, everything it has ever experienced, everything its biology allows it to perceive, describes 5% of its environment, and it is making navigation decisions based on that 5%, confident it understands the ocean well enough to cross it. This is not an argument that dark matter and dark energy present additional physical barriers to interstellar travel on top of the ones already cataloged. They may or may not. The honest answer is that we do not know, because we do not know what they are. And not knowing what 95% of reality consists of, while simultaneously concluding that our physics is complete enough to rule out any possible shortcuts or solutions, requires a degree of certainty that the data does not support. Now the deepest layer. Every barrier examined in this entire story: the speed of light, the energy requirements, the radiation environment, the structural behavior of matter under vacuum and cosmic ray bombardment, is a consequence of the universe's fundamental physical constants. The speed of light, c, the gravitational constant, g, Planck's constant, h, the fine structure constant governing electromagnetic interactions, the masses of the electron and the proton. These numbers are not derived from any deeper theory. They are measured values, inputs to physics rather than outputs. They are simply what they are, and the universe that results from their specific combination is the one we inhabit. Physicists have run the calculations on what happens if any of these constants shifts by even a fractional amount. Change the fine structure constant by 1 part in a million and stellar nucleosynthesis, the process by which stars forge carbon and oxygen from lighter elements, ceases to produce the chemistry life requires. Alter the ratio of proton mass to electron mass slightly, and stable atoms cannot form. Adjust the gravitational constant marginally, and stars either collapse immediately or never ignite. The universe is not just compatible with life. It is balanced at a knife's edge of parameter values that permit complexity, chemistry, and biology to exist at all. The anthropic principle describes this observation. The physics confirms it. The same constants that make life possible also set the speed of light. The same constants that allow stars to burn also determine the energy requirements for interstellar travel. The same constants that permit biology also establish the radiation environment that biology cannot survive at interstellar speeds without shielding that creates mass penalties that cannot be overcome. The universe did not separately decide to permit life and separately decide to make interstellar travel impossible. Both outcomes flow from the same set of numbers. The same physics that assembled you, assembled the barrier. Whether this is design or accident, whether the constants are what they are because of some deeper principle, or because of random selection across a landscape of possible universes, the result is identical either way. The universe is configured precisely to produce life, and it is configured, with equal precision, to confine that life within the gravitational boundaries of a single stellar system. Every civilization that has ever existed anywhere in this 13.8 billion-year-old cosmos has faced exactly this situation. Whatever they achieved technologically, however far their science progressed, however long they persisted, the same constants governed their physics. The same walls enclosed their ambitions. They were alone in their solar system the way we are alone in ours, and no amount of intelligence or determination changes the arithmetic of C, G, and H. Each civilization an independent experiment, isolated, unreachable, conducting its science, asking its questions, looking at the same stars from an entirely different vantage point, arriving at conclusions no other civilization will ever read. The universe has been running this experiment for 13.8 billion years. It has run it in hundreds of billions of galaxies, across hundreds of billions of star systems. Every instance of the experiment is separated from every other by distances that the experiment's own physics prohibits crossing. And so the question that has driven this entire story, can we travel to other stars, turns out not to be the question that matters most. It was never really about whether the engineering was good enough, or whether the fuel was dense enough, or whether the ship was strong enough. Those were symptoms. The real question, the one that every civilization eventually arrives at when it traces all the symptoms back to their source, is this: what do you do with the one planet you have? The universe has 13.8 billion years of patience. It constructed complexity across 4.6 billion years of Earth's geological history before producing anything that could look up and wonder about it. It can wait for an answer. The stars are not going anywhere. The light from 100 billion galaxies arrives every clear night without being asked. The cosmos is not withholding itself. It is simply waiting to see what we do with where we already are.